learning about the gradient intercept form for a straight line or a linear function, and our learning goal is to understand how that differs from what we saw previously with direct proportion. So we can see a red line, it's a straight line graph, and you can see on the side here the form is y equals mx. That's the form, and we looked at that previously as direct proportion. Y equals mx, and that's from the previous work. So we can vary m, and it changes the rate of the direct proportion because it changes the gradient. Looking at that, so you can see the m, and if I change that, okay, and it changes the gradient. It can be negative or positive. Okay, steeper, less steep. It can be falling like that one, rising or falling. But what's always the case is that it doesn't matter what you have for the gradient. What do you notice about the y-intercept? Where does it cut? It always cuts at 0, 0. So it always cuts through 0, 0. Always. So any direct proportion, the y-intercept always goes through 0, 0, the origin. But if we look at a second sort of function, it has the form y equals mx, like the red one above, but it's got a plus c on the end, so y equals mx plus c. And you'll see that when I turn that on, it's green. Hopefully you can see that, and it's set directly over the top of the other one. So is there no difference? Well, you might see that c is set to 0. What if I change that? Now you can see the other line. So C changes the position of y equals mx. In fact, it stays parallel. It's like train tracks. So it hasn't changed the gradient, but it's like it slides it up and down. If it's negative, so it's at -2 at the moment, alright, it's slid down. If it's 0, it's back to where it was, and if it goes up, you can see C increasing. C is actually the value of the y-intercept. So you can see that right there, we've got, where the cursor is, you've got C equals 4. Alright, because the y-intercept is 4. So C equals the y-intercept. Okay, that's where, from our previous work, that's where the line cuts the y-axis at the y-intercept, and that's the value of C. Let's have a look. So C is set at 4 at the moment, and the y-intercept cuts the y-axis at 4, and that, as a point, we would call that 0, 4, wouldn't we? Okay, so that's why this y equals mx plus c. It's the form for the gradient intercept form. Okay, they're always in that form. So an example might be if you get somebody to repair an appliance like a washing machine or something that's repairable, and they come out to your home and they charge you a call-out fee of $120 and then $60 per hour that they work. And you can see we've got that graph here where we've got time. As time goes by, the cost goes up. So we've got a example. It is direct proportion, except for that it doesn't go through 0, 0. It goes through 0, 120. We can see there. So it goes through the point 0, 120, which corresponds with the y-intercept. So that's when time is 0. 60 times 0 would equal 0. 0 plus 120 is 120. So the graph can't start at 0, 0. It starts at 120 because of the call-out fee. And then it goes up. And the rate at which it goes up is the same as the gradient. So for every 1 hour it goes across, it goes up 60. So for every 1 hour it goes across, it goes up 60. So 1 hour across there and $60 up. So that's the gradient. So it's important to note that in general, the gradient intercept form is written as y equals mx plus c. That's the form. So you'll get numbers in there for m, which is the rate or the gradient, and you'll get a number there for c, which is the y-intercept. Occasionally books we might use the letter b, but I don't think you have to worry about that too often. That's more of an American thing. It's just a letter, it's just a symbol. So m is the gradient, the slope, and c is the y-intercept where it cuts the y-axis. And that's why it's called the gradient intercept form, because it has a varying gradient and a varying intercept from line to line. And these are forms of a straight line, and it's the most common form of a straight line equation. There are other ones. And it's similar but not exactly the same as the previous direct proportion that we use, which had y equals mx. The difference is that c is usually not 0, it's usually some number which makes it translate up or down. So as we saw on the graphs before, if we keep the gradient the same, you can see the gradient's always 2, m is 2. They all have the same slope, all these family of lines here. Okay, so the difference is that the intercept has changed in each case. This one here has got an intercept of 0. So the first family, it's only the y-intercept that changes, and you get parallel lines. And each line, if we start at y equals 2x, this one here, and we look at the 2 to the left, they've been moved up by 1 and 2. So it translates the line up, or slides it up. -1 will slide it down, so the y-intercept is at -1, and -2 it slides it down another one, so that the y-intercept is at -2. In this one here, we've got different gradients but the same y-intercept. Look, they all go through the same y-intercept because they've all got +1 on the end, and the difference is the gradient is changing in each case, and you can see that's like I showed you on the video. So go back to the earlier part of the video. They all go through the same place on the y-axis, the same y-intercept, but they have different gradients because the m is different. Looking at a couple of examples before you try some yourself. Now these next few examples, some of them we will be doing what you see here. We'll be sketching a graph using the gradient intercept method, and what we have to do is locate two things. You need 2 bits of information when we're looking at a straight line, and you might have heard me say that in the past, 2 pieces of information. Now the 2 pieces can be the y-intercept and also the gradient. So if we have the y-intercept given, we know a point, and if we have the gradient, we can sketch that in because the gradient is rise over run. So this would have a rise of 2 for every 5 that it runs. So we can do that because a gradient stays the same. So that means we go up 2, you see there, we go up 2 for every 5 we go across. And we can keep doing that. We go up 2 and then 5 across, and it's a bit like stairs and connecting them up. And this is what we're going to do. First example we'll show you is find the value of the gradient and the y-intercept and then sketch their graphs. So we've got 3 things to do. We've got to identify the gradient first, and if we're given this equation, well, if you paid attention earlier on, gradient is m. So this is mx plus c, so y equals mx plus c. We've got m is clearly 2, so the gradient is 2, which we can write as 2 over 1. You think, why would I do that? Well, it actually becomes handy later because that's rise over run. So the gradient is 2. The y-intercept, well, the plus c, now you're thinking that's -1. Alright, there it is there. -1. So what, plus c, minus, what's going on? Well, how do we get a -1? We go, -1 is plus what? -1. So c is the y-intercept, it is -1. So we found the second bit of information. We now have those 2 bits of information that I mentioned. Remember, you need 2 bits of information to sketch the graph, and that's what we're going to do now, sketch the graph. Okay, let's have a look. We start with the easiest to start with the y-intercept first. So -1, that means it cuts through at -1 on the y-axis. You can see that down there, the point 0, -1, that's our starting point. We need a point to start with. We need to know the slope or the gradient. It's 2 over 1, so that means rise is 2 and the run is 1. So it goes up 2, then across 1, and it keeps on doing that. So it goes up 2 and across 1. You can see that if we can get the second point here by going up 2 and across 1, or across 1 and up 2. It doesn't matter about the order. They've done the run and the rise, and it still works. If you go rise 2 then run 1, you still end up in the same place. And that's our sketch. A harder one now. This one requires you to rearrange first because it's not in the form y equals mx plus c. Alright, so remember y equals mx plus c, the gradient intercept form, is how we are rolling today. This is our topic, so we're not in that form. We need the y by itself on the left and the x on the right. So if we subtract x off both sides, remember we've got to do the same to both, you can see what happens there. We've got 2y becomes isolated by itself, which is good, but there was no x on the right side, so we've taken 0x on the right side. We've got 0x take x, we end up with -1x, and that's the 6 from before. Then let's have a look what happens on the next line. We have to divide both sides by 2 because we want 1y, and we've got 2y there. So remember, you've got to do same to both sides. We've done a lot of work on solving equations, and here it is in action. So you divide the left by 2, you get 1y. Divide the right by 2, you've got to divide this whole expression here by 2, and that's why it's all over the same vinculum line. See? Now, that's pretty much the answer. You might see that they've written it in a different form. Well, you can go 6 divided by 2 is 3, so that makes sense. And -x on 2, another way of writing that is -1/2x. So you've got -1/2x plus 3. To draw that, we've got to identify the gradient. The gradient is mx, and you can see that it's -1/2. Now, the run is always positive. Remember, it always goes from left to right, so it must be the rise that's negative here. So it's going to be a fall. So it's going to go fall 1 for every 2 it goes across. What's the y-intercept? It is 3. So let's draw that. We've got to start with the y-intercept, which is 3, so the point 0, 3, and it'll fall 1 for every 2 it goes across. So you go fall 1, 2 across, fall 1, 2 across, fall 1, and 2 across. They've done it the other way around. You can see here they've actually reversed the order, and you get the same result. And you get a second point there. You connect the first point.